So in this video, we'll solve a second problem on the thick cylinder. Okay, it is same as usual. In the previous video, problem 1 we solved here, but little bit the data changed, and you have to stress distribution also. It will be little bit change here. Some values are changing here. Okay. First, we'll go to the problem here. What the data is given: a cylindrical pressure vessel with inner and outer diameters. He's given inner diameter and the outer diameter. So inner diameter is 180 mm and outer diameter is 220 mm. First we'll go to the data here. So inner diameter di equal to 180 mm. Therefore we want the radius to draw the sketch here. So Ri is 90 mm, right? 90 mm. And outer diameter is d naught equal to 220 mm. Therefore R naught is equal to 110 mm. Okay. These two diameters respectively is subjected to, and this is the outer diameter and the inner diameter, 180 mm and 220 mm respectively, is subjected to an internal pressure. He is subjected to an internal pressure of 10 MPa. It is inner wall. That is, can I write it Pi equal to inside, that is x equal to Px. That is Px equal to how much? 90 mm, right? 90 mm. How much is given here? 10 MPa. 10 MPa. 10 MPa is nothing but 10 Newton per mm square. When x equal to 90, inner radius. Okay, 90 mm. Taking the circumferential stress at the inner wall as 25 mm. He is given the circumferential stress at the inner wall. Okay, inner wall is 25 MPa. It is in tension. We are drawing in the tension side only. So he is given tension. So how should I write here? That is sigma c at inner wall. At inner wall, it is at x. That I can write it as sigma c at x equal to how much? 90. It is inner, right? At x equal to 90 is how much is given? The 25 MPa. 25 MPa. Determine the maximum value of the external pressure that can be applied. External means when x equal to how much? When x equal to R naught. X equal to R naught, it is 110 outside. First we will draw here, then we will come to know. That is sigma c naught. Outside is how much? That is sigma c at x equal to 110 mm equal to how much? He is asking the first bit here. Determine the maximum value of the action. That is first one. This is first one that can be applied. And second one is circumferential stress on the outer surface. Circumferential stress on the external pressure. First one is external pressure. Sorry for that. External pressure is the P at outside, right? P at outside, that is P equal to P at x equal to 110 equal to how much? First bit. Second one is circumferential stress at the outside equal to P. The circumferential stress at x equal to 110 equal to how much? This is, they are asking the data here. Okay. First we will try to draw the sketch here. How much possible? We will mark it there. First I draw here. This is inner radius and this is outer radius. Okay. Here is the center, and just from center, this is the center mark here. Okay. And first this we will mark it as Ri. That will be at x equal to how much? At x equal to, the radius is how much? Inner radius is 90 mm. This is 90. And this one is R naught. That will be equal to x equal to 110. The outer radius is 110. Okay. These two we mark here. Next, anything else? Pressure at inside he is given. Always pressure distribution we are marked in the downside, and stress circumferential stress distribution we are marked it in upper side. So now he is given the pressure distribution at x equal to 90. When x equal to this is 90, pressure is how much? 10 MPa. Just mark here, the pressure is 10 MPa. From here to here, the pressure is 10 MPa. Just Pi equal to 10 MPa. Later we will draw that. Okay, so anything else? Circumferential stress at the inner side. This is circumferential stress distribution. This is the inner wall. At inner, it means at x equal to 90, 25 mm, 25 MPa. Just mark here also the one of the 25 MPa. That is from here to here. Just mark it 25 MPa. That is sigma Ci equal to 25 MPa. These 1, 2, 3, 4 data is given. We mark now. Remaining we have to calculate here. Okay. Now how we start to calculate here remaining values, because we want the P naught outside and we want sigma C naught. Okay. We will use the Lamb's equation, right? So we know that the Lamb's equation. From that we will calculate the unknown values here. From Lamb's equation, what are the Lamb's equation here? P at x equal to b by x square minus a. This is one equation. Similarly, sigma C, circumferential stress at x equal to b by x square plus a. This already we derived. Okay. Now try to find out the a and b are the constants by applying the boundary conditions, by given whatever the data is given here. Okay. First apply when Ri equal to, when x equal to 150, 90, R equal to Ri, and how much is the pressure is given here? That is P equal to 90, Pi, that is R equal to Ri, and P equal to Px equal to P90 equal to how much is given here? 10 MPa. This is one boundary condition. When x equal to 90, pressure is 10 MPa. Next, anything else? When again same is given circumferential stress at x equal to 90 only, in the inner side only. Similarly apply when x equal to 90, sigma C equal to sigma Ci x, sigma Ci, that will be equal to sigma 120, sigma 90 equal to how much they are given here? That is 25 MPa. This already we have noted down here, and here also he is given. Apply these two conditions on this equation. First I am applying first condition, x equal to 90, that is, therefore this equation becomes P pressure at 90 is 10 MPa. The left side is 10 MPa, and B divided by x is how much? That is 90 mm, right? X is distance 90 square minus a. This is one. After applying these boundary conditions, this is boundary conditions. Next, second one. So stress is how much? It is 25 MPa at a distance of 90. Therefore 25, here I am writing the b by x square. X is how much? It is again same in the inner wall. It is the 90 square plus a. Okay, call it as this one as a, this one as equation 1, and this one as equation 2. This is a and this is b. Now from 1 and 2, solve 1 and 2, you will get the unknown values a and b. Okay, if you add, these two will cancel, b will get, and again the substitute the b value in any one equation, you will get the a value. Okay, I will go directly the solving here. Solve 1 and 2. What we will get here? That is, after solving 1 and 2, we will get first b value. B equal to 141750. 141750. Okay, this is a constant, no dimensions. And a equal to how much? Again substitute b value in any one equation, we will get the a value. Okay, a is 7.5. These two we will get here. Okay, now we can come to what we want to calculate here. He is asking the when x equal to 10, how much is the pressure, outside pressure? we go to the same here in these two equation. Which one we have to choose? In the Length equation we have to choose this one here, right? Substitute x equal to 110, x equal to 110. We know b value, we calculated a value, and x equal to 110. We will get the pressure at 110. Similarly, circumferential stress at 110 at outside of the wall R0. Okay, substitute, we choose this equation, Length equation. Substitute x equal to 110, and here also 110. We know a and b value, we can calculate here. Okay, now I will solve these two here. I will remove the boundary conditions and we will try to solve. Therefore, when x equal to 150, we have to calculate, that is we have to calculate the px, that is p at 150 equal to b by 150 square minus a, right? We need the p at 150, sorry 110, it is 110, outside is 110, sorry for that, 110 here also. When x equal to 110 mm, here also 110 square, okay. Substitute, b value is how much? 141750 divided by 110 square minus a is 7.5. Calculate the right side and we will get the pressure at outside, x equal to 110, or it is the P naught here, that is P naught. Okay, therefore P at 110, after calculation we will get 4.2 MPa. Now come to the sketch here. So outside here it is 10 is there, in the inside it is 10, here it is, here I will mark is P naught or P at x equal to 110. How much we will get? 4.2 MPa, Newton per mm square. Okay, this is the value. Now we join Pi and P naught. Okay, these two values we can join, right? This is the P naught value, and this is the pressure distribution along the thickness. Here 4.2, here 10, little bit down, this is up. Okay, next come to the circumferential stress. Here in the inner valve it is 25 MPa. We will calculate the outer valve. For that we have to use this equation, right? Use the second equation of the Length equation here. Okay, when x equal to same, when x equal to we want the outer, x equal to 110, sigma c at 110 we want, that will be sigma c naught, both are same, equal to b by 110 square plus a. Now substitute b value, you know b value 141750 divided by 110 square plus a. Okay, now the simplify and calculate how much we will get, that is sigma c at 110 equal to sigma c naught equal to substitute and calculate, we will get 19.2, that is 19.2 MPa at the outer wall. Now come and mark the point on the outer wall, circumferential stress on the upper side. So here 25 is there, so little down it will come here. Okay, 19.2 I am marking here, that is sigma c naught equal to 19.2 MPa. Now join the one more, 25 to 19. Okay, 25 to 19. This is the circumferential stress distribution. If you see the sketch, normally inside is more circumferential stress and the pressure distribution because of the fluid present in the inside of the wall. As the thickness goes on increases, its circumferential stress goes on decreases, as well as the pressure goes on decreases here. Okay, see here the 19.5 and here 25, here 10 is there maximum and here 4.2. Okay, this is how you have to draw the pressure distribution along the thickness. This is your thickness. Thickness is how much? The R0 110 minus 90, how much? That is 20. This is 20 millimeter thickness here. Okay, this is how you have to sketch the distribution and calculate the unknown values by using the Length equation.